Welcome back. In 5.7, we get to work a little bit with financial models. So let's say that we open an account and we invest P dollars. Our interest rate is given as R, and it's compounded n times a year. So we're going to pick up a nice little pattern from this. Number of compounding. So 0 compounding, so this is the day we open account. The amount in the account, A, measured in dollars, is just P dollars. Our first compounding, now the amount in there is not just the P dollars that we put in. We also earn some interest in that. It's an R percent interest rate, but it's compounded, it's split among n times a year. So R over n times P. So this is what we had. This is what the bank put in. We can even factor that and turn it into P times 1 plus R over n. So then we'll go with our second compounding. Now our account balance is what we had in there before, plus what the bank is going to put in there in terms of interest. So they're going to again give us R over n. So our interest rate, if we earned 12% interest, good luck finding that, compounded monthly, each month you're getting 1% then, times our previous balance. Again, there's a little bit of factoring we can do. Each one of these has a P times 1 plus R over n. I'll factor that. That would leave a 1 here and a plus R over n in the second spot. So then our new account balance is P times 1 plus R over n squared. We have that same factor twice. Our third compounding, again, we get to keep all the stuff that was there before, and the bank is going to give us R over n interest paid on the previous account balance of P times 1 plus R over n quantity squared. You should see the same game developing here. We'll factor a P times 1 plus R over n squared, and also have another 1 plus R over n. So 1 from here and R over n from there. And hopefully you see the pattern at this point, that then our account balance is in general for the nth month going to be P times 1 plus R over n to the n times t, number of compoundings per year times t years. Here t equals, unless denoted otherwise, so unless they give us the interest rate in terms of it's a 2% monthly interest rate, if they give us an APR or an APY, A is annual, measured in years. So unless denoted otherwise, T is going to be how many years. So n a year for t years. Total number of compoundings. Now we can also build on that. Some accounts earn what's called continuously compounded interest. So we're going to let x equal n over r. So recall from the previous page, a is worth p times 1 plus r over n to the n times t. So a few different versions of that same equation from our let line. N is worth x times r. And I notice here we have an r over n. So if I want r over n, I'd have to divide both sides by both x and n. So then r is worth, or I'm sorry, r over n is worth 1 over x. So then a little substitution. R over n is 1 over x. N is xr. So some of this should look familiar. The familiar part I'll put in red here. And if we let x go to infinity, this came up with a number we saw earlier in the chapter, e. So in other words, the number of compoundings goes to infinity, x will also go to infinity. So those are the two major formulas that we use in this section. And we can look at doubling time, or just how much do we get there after a certain amount of time. So we'll start with a doubling time problem. So you might have noticed here, I didn't tell you how much money we invested. I just want to know how long it'll take to double our investment. The only simplifying assumption we're making with this one is we're going to assume that we didn't incur the wrath of the bank by having some amount that's below whatever minimum that they set, that they're not going to start charging us fees for having this account. So we're going to assume that we clear that hurdle, and we just want to know, okay, how long would it take to double the money? How long would I have to just park my money in the bank? And you'll see in a second why I didn't actually care how much money was in there. So if we've doubled the initial investment, so P is our initial investment, it's always our initial value, the principal. If I double that, that's just 2p. Now, they didn't say we're compounding continuously, but they said monthly. So we're using the first formula. So our new amount is going to be twice our original. So p times 1 plus our rate, 3%, and we go to decimal form. over n. Monthly would be 12 compoundings a year to the 12 compoundings a year for t years. So there's why it doesn't matter. If I divide both sides by p, the initial principal doesn't matter. So it'll take you the same amount of time to double $100 to $200 as it would take to double $1 million to $2 million. So then 2 is worth 1 plus 0.03 over 12 to the 12t power. Now, if this number comes out nice and clean, great. If it doesn't, leave it in this form. Don't round it. We're only going to round at the very last stage of the problem. The variable we have is in the exponent. We're going to need logs to get the variable out of there. So natural log of 2 is natural log of 1 plus 0.03 over 12 to the 12t. Exponent becomes a factor. So natural log of 2 is worth 12t natural log of 1 plus 0.03 over 12. So then I'll divide both sides by everything but t. So then t is natural log of 2 divided by 12 natural log of 1 plus 0.03 over 12. Word problems, when they're asking how long something takes, this is a time when you would do an approximation as well. All right, we'll start with natural log of 2 upstairs, close it up, divide by. You're going to need to open a parenthesis to tell the calculator that all this stuff is in the denominator. So 12 natural log of 1 plus 0.03 over 12. Close that up. Close the other one, telling it that we are done with the bottom of the fraction. So t is approximately 23.1. And any word problem you want to answer with a sentence. Employers are really on the colleges, South Suburban included. They want students that graduates that can write well. They're really searching for that skill. Practice it now. Write a sentence. So it'll take 23.1 years to double the investment. Okay, so this next one, we're going to invest, let's say, $10,000. And let's say our rate is 4.25%. And let's compound it. Let's say we leave it in there for 20 years. So let's run through first if it were quarterly. So quarterly, there's 4 quarters in a dollar, 4 quarters in a year, 4 times a year. So our new account balance, principal, $10,000 times 1 plus our interest rate of 4.25%, 4.25%, in decimal form, 0.0425. Compounded quarterly over 4 to the 20 by 4. And it's TI's problem after that. So then 10,000 by 1 plus 0, 0.0425 over 4, close it up, and raise it to the parentheses 20 times 4, or just take care of that multiplication. One of the most common sources of calculator error in this is not putting that times 4 in the parentheses. Then it's reading it as raised to the 20th and then times 4 instead of a 4 in the exponent. Okay, so then at the end of 20 years, now we're looking at having $23,291. And we in math class would round that to 80 cents. Banks actually would truncate that. Truncating means basically no matter what number comes in the thousands place, they round it down to 0. They never round up to the nearest penny. So 1% at a time, that doesn't seem like much, but if they have thousands of transactions, over thousands of customers and locations, that does actually add up quite a bit. All right, so the balance after 20 years is dollar signs go in front of a number, not after a number. I have no idea where that came from, that I started seeing that over the last 2-3 years. Dollar sign goes in front. $23,291.80. Let's just change one little thing. Let's change from quarterly, let's change it over to monthly. So instead of compounding it 4 times a year, we're going to compound it 12 times a year. A lot of it's going to look the same. 10,000, 1 plus 0.0425. Instead of over 4, over 12, raised to the 20 times 12. Now we don't have to reinvent the wheel with this. Second and entry brings back our previous calculations, but where we had a 4, I'm going to delete that and insert a 12. And same thing here. I'm going to delete that 4, insert a 12. So not terribly different. So in part B, we have the same answer sentence, but it ends with $23,361.36. And then let's change it to continuously. That one will look a little bit different. So on that one, continuous, A equals 10,000, the principal, times e to the r times t. R is 0.0425, and t is 20 in years. So 10,000, e raised to the, and it should open a parenthesis automatically for you, 0.0425 times 20, and close it on up. Make sure it knows that both those things are in the exponent there. So then our last answer sentence starts out the same, only this time our ending balance $23,396.47. So again, not a huge difference, particularly when you look at this being a not insignificant amount of money and left there for 20 years. The amount of difference is relatively small. It's a little bit less than you would expect, changing up how often they compound the interest. It will give you different values, just not extremely different values. All right, so on 5-7, I would try out 7 through 22, 39 to 43 on the odds, and number 49. And again, I'll try to piece together a similar assignment for the My Math Lab fans as well. If you have questions, please get in touch. Otherwise, I'll see you next time. Stay safe out there.